In this setup, we are going to measure FRF data for the purposes of frequency-based substructuring, which is a technology that allows us to virtually couple source components to receiver components in order to predict MVH performance. So the component that we will be focusing on is this tire wheel source components that we use for predictions of structure-borne road noise in virtual vehicles. And in order to perform this prediction, a quantity that we need are the impedance FRFs of this tire wheel source at the connection interface, which in this case will be defined as a virtual point that we specify at the center of the tire wheel. Now, an impedance FRF can be compared to a driving point FRF in the sense that to get this impedance, we need to excite and measure the response of the tire wheel at our connection itself. But as you can see, for the tire wheel, the virtual point at wheel center is essentially a hole. So we don't have any way to directly excite or measure response at the connection interface directly. So the technique that we will use instead to obtain this data is called virtual point transformation, where we provide excitation, in this case using a Q-Source's integral shaker connected to a QTRX in-plane excitation adapter, which allows us to connect the shaker on up to 16 different degrees of freedom. And using this setup, we will excite different points around the wheel center, and at the same time, we will measure the responses at, in this case, triaxial accelerometers, of which we have also located a few different ones around the connection interface. And the principle behind virtual point transformation is that by assuming local rigid behavior of the structure between the connection interface and the measurement points, we can essentially geometrically recalculate all that measured transfer function data to impedance FRFs, which are acting exactly on the virtual points at the connection interface. Now, one last critical ingredient to performing these measurements is the usage of a virtual geometry, for example, coming from CAD, in order to create essentially a digital twin of the measurement setup that we have created here. And the basis for this is that virtual point transformation is a geometric recalculation of our measurement data, which means that using such a digital twin of the instrumentation setup, we can much more accurately and conveniently extract high-quality information on the relative position of an excitation or response sensor compared to the virtual points.